Okay, so let's commence. So maybe I should just share the screen as well, right? So let's do that. So good afternoon. Are you able to hear me?
Good
Yes, sir.
afternoon, sir.
Yeah. Okay. Good. So I can hear you well. All right. So let's So let's get started. So we finished the discussion on perceptron. Okay. So very quickly I will just mention that. So perceptron discussions are over. So what we so the algorithm is there. You remember the algorithm. So you randomly initialize w, and then there is a loop till all points are correctly classified, and then you had I won't write full details, but there was a step like wk plus 1 is equal to wk plus some delta wk, right? So delta w, whatever I called it, I don't remember what I called it, but some delta. Okay, so now we saw this, and then we also understood that so this is the variant which I'm talking about. So here you also have the state that xi is equal to minus xi if yi is equal to 0. So this also has been done. So for this particular setup, so we also have cost function. So what we have is cost function, or goodness of it, jw is given by negative xi transpose w. Okay, I'll write it as wi transpose x, but they are both the same, w transpose xi. Okay, and we only sum those i's such that w transpose xi is less than 0. Okay, so this is what we had, and we also saw there are two versions of this, which is like regular gradient descent. Okay, here we use the full gradient, right? The full gradient is used, and then the stochastic gradient descent. Okay, what am I writing? Gradient. Okay, so here what we do is we say w is equal to wk plus 1. So the next new one, w new, is equal to w old plus some eta times xk, right? So this is what we had done, and we chose the eta equal to 1 in our regular perceptron algorithm. So this is all the things that we saw yesterday. And yeah, so we saw this, and now we will start a new topic which is called as regression. Okay, so we are going to start a new topic which is called as regression. So regression is a problem where classification problem we have all seen. In the classification problem, the labels y, they belong to 0 1, whereas in regression problems where the label y will belong to r. Okay, so you are trying to learn a function from x to y. So suppose there is a y which is equal to some function of x plus a possible noise. So this is unknown. We would like to learn this, right? So this is we would like to learn this function, and epsilon is just saying that there could be noise. Okay, so this is the goal of regression problem. Okay, so we would like to learn this function so as to best fit it, right? So what you are given is the data sets, which is xi, yi, and I going from 1 to capital N. And here again I don't write the tilde, but it is an augmented feature representation. I always have an augmentation here. Perhaps I will write it. That's fine. Okay, so now there are many examples of regression. For example, the standard example that is given is of house price. Okay, so the house price, so you would like to learn the house price as a function of various features. So features could be x1, the first feature could be area, x2 could be uh, area means area in meter square, for example. X2 could be the number of bathrooms, and so on. And then there are many such features, perhaps xd features are there. Uh, and then your y, so for a particular set of samples, so if there is a house which is let's say 100 square meters with the 3 bathrooms, and then so all these features are there, and there is a price that is given to you, maybe it is 200,000 rupees, right? So this is in uh, rupees, in thousands of rupees. So into 200 into this amount, that is the price of this house. So like that you are given several houses and your goal is to learn it. Okay, so when we talked about perceptron, so let me just remind you. So in perceptron, when we looked at perceptron, what we were doing is we had some points. Okay, let's say these are all class 0 points, these are class 1 points. We are the diagram that we drew for perceptron was we have to find a hyperplane that separates them. So these are all, let's say y equal to 1 point, these are all y equal to 0. So this was the goal in perceptron. We want to be able to do it. And when are we happy? Yes, when are we happy with a perceptron learning algorithm?
All points are correctly classified.
Yes, yes. So now I will draw a very similar figure. Okay, I will draw exactly a similar figure for regression as well, but I will say how it is different, because though it looks very silly, but I may get similar points but when I plot it, right? But these are both features. So this was x1 and this was x2, could be like height and weight, and this cat divides the region into two parts, y equal to 1, y equal to 0. That was perceptron. In regression, what we are trying to do is, this is house price. Okay, so suppose if I want to learn house price as a function of uh, area. Okay, and then my goal will be something like this. If so, if it's a line, suppose like I choose the function f of x that I am trying to learn, which is a some w transpose x, some line. Okay, I want to learn it as a line, then it is called as linear regression. So is the two difference between the two problems clear?
Yes.
Okay. Okay, so this is your y and this is your x. So here we don't show y, here both the features are written. All we are trying to do is we are trying to divide this area into two half spaces. One half space has all y equal to 1, one half space has all y equal to 0. That was the goal in perceptron. Okay, so for a perceptron we saw what was the goodness of fit, right? We all saw that. So what do you think should be the goodness of fit for regression?
The
Minimum
distance
error.
should be minimum.
Two people spoke. Who was the other one? Tanuja, did you say?
Yes, so minimum error.
Okay, and what is an error?
Uh, the difference between actual price and the predicted price.
Yeah, so suppose if, yeah, so let me just try to explain that a little bit. So suppose you are given, these are the points that are given to you. And one of the functions that you learned, suppose this was one w and another one was this w. So roughly you can say that, so this is let's say choice 1, right? This is choice 2. So choice 2 is better because it is minimizing the error. So what is the error? So the error is these blue bars that I am drawing. That is the error at each point. So for example, there is a positive error in these areas, there is a negative error here. Okay, so if I just take sum of errors, that is not really good. Why?
Positive and negative may be large, but they can cancel out, and
Yeah,
so we can get a small.
yes, positive and negatives may be large, but they can still cancel out, right? So instead, what we will use is what is called as root mean square. I think it is not root mean square; it is called mean square loss. Okay, or LMS. So I think it's called as LMS because loss mean square, I think. Yeah. So this is called as LMS loss. So what do? So we have J of W as we had for the other case. Here J of W will be, I will just take 1 over half, that this constant doesn't matter, right? So you multiply by something, it doesn't matter. But here we will look at f of xi, okay? And since we are saying it's a linear function that we want to learn, so it is W transpose xi minus yi squared, I going from 1 to n. Okay, so this is my J of W. This is my loss. Okay.
So don't we take mean here somewhere, or like it can
I
be?
mean, by n you want, you can do, but we don't take typically.
Okay, sir.
It doesn't matter, right? Whatever I multiply with this, if W
Yes.
minimizes, yeah. So it really doesn't matter how you take, but we typically take just 1 over 2. Somebody has a question, looks like. Siddhant, you raised your hand. Do you have a question?
Yes, sir. So we discussed perceptron because it is orthogonal to our choice of linear regression, something of that sort.
No. I just no. Perceptron is like Perceptron is a good algorithm to understand what is meant by classification, a simplest learning algorithm. So for that purpose, we learned perceptron. Okay, so don't get confused, Siddhant. So see, this is so here this entire two-dimensional plane is a
Sir,
plane of features.
Sir, your voice did cut off for some time in between.
Is that only for Siddhant, or others also felt like that?
No, sir.
No, sir.
Okay. Any case, it didn't get cut, he's saying, but let me repeat anyway, Siddhant. So what I'm saying is, for a classification problem, you have two features, right? So let's say height and weight, and you want to identify people who are heavy built. Okay, so this is like that problem. You want to divide the entire feature space into regions where you will say somebody is heavy build, and into a region where you will say somebody is lightweight. Is that okay? This is what is the goal in classification.
Yes, sir.
In regression, what you want to do instead is your entire feature space, even if there are several axes, suppose there was area and then number of bedrooms. Okay, the goal here would be to predict the price. Okay, so it's like trying to learn a function of features. Okay, Siddhant? You would like to learn y as a function of all the input features. Is it clear? I'm not able to hear you. I'm assuming that it's clear. Okay. All right. Okay. So I was disconnected. Right? Hello. Are you able to hear me? Hello, can you hear me?
Yes.
Yes, sir.
Yes, sir.
Okay, so let me just change to my other network. Maybe that is better. I don't want to get any more interruption. So let us see. So okay, so I have changed network. I will just stop sharing my video because this is a mobile network. Are you all able to hear me well?
Yes, sir.
Okay. So Let's see. Okay, so Siddhant, where were we? Did you hear what I was saying for this
Yes,
explanation?
sir. You said that for classification we try to separate things out, and for regression we try to get in like predict the best we can without by decreasing the
Errors.
error.
Okay, so there is no connection between these two. I am just making it extremely clear. All right.
Okay. Yes, sir.
Unless you have a same feature set where you want to do a classification as well as regression, as such there is no connection. Okay. All right. So this is the LMS loss. Okay. So this is given like this. So now what we would like to do is we would like to find the best W. Okay. So the goal is to find best W. Okay. Find W such that uh, JW, this W is equal to arg min of JW. Okay. So one thing that is kind of interesting here, who can tell me this? So if I try to minimize this, will there be multiple minima,
No, sir.
and why is that?
It's a it's a convex function.
Yeah, it is a convex function. Okay, so there will not be multiple minima because it's a convex function, and the way to check that, so is to take the second derivative of this, and when you take the second derivative of a function, so second derivative of j with respect to w, this is going to be a Jacobian, because I think, I don't know whether I don't at least in optimization you would have seen, but any case, so when you take the second derivative you will get W transpose W, and this W transpose W is a positive semi-definite matrix. Okay, and when that is the case, you have that J of W has a unique minima. All right, so I will ask you to do it for a particular simple problem. I will ask you to draw the contours of this. So what will happen, you will draw for a simple case with W0 and W1, and you will draw this JW, and it will turn out that it will have contours like this, and this will be the minima. Okay, so we will do that at some point. All right, so now how do we find the W? How do you get the best W such that JW is minimized? Yes, someone wants to suggest some ideas?
So we can
Derivative.
try to find an update rule like we did in last class by
Yes.
minimizing the W.
Yeah, so that is one definite way. So that is like gradient descent, right? So one is that approach. Any other approach have you seen?
So just the derivative equal to 0,
Yes.
but it will require some math.
Yeah, so that is true. So there are two approaches whenever you are given an optimization, unconstrained optimization problem. There are two approaches one can do. One is gradient descent. Always you can use this. And second one is to set gradient equal to 0 and try to get analytically try to get W. Okay, and try to solve for W. So we have used gradient descent in perceptron. Where have we used this approach in the course so far?
EM algorithm.
Yes, very good. So in EM, in all, basically MLE, we have used there. EM, MLE everywhere. Okay. So you have already seen both the approaches, but I will show you first the gradient approach, and then I will show you even the MLE approach. Both are very important, and we will do that today. Okay, as far as possible. All right. So what we will do first is we will convert this into matrix notation. So your y your y1 to yn, the n data points, I will write it as a huge vector y. Okay, this will have first data point, second data point, and all the way till n data points are here. This is your y. Okay, so this is n rows and one column. So this is y, and w transpose x, I would like to learn this y, okay, as a function of w transpose x, right? So this is y. So this is on the one side what you want to get, comma this is, but we want to get it as w transpose xi. So what we will do is we will look at all the vectors in this manner. So w1 to wd plus 1 will be here. Okay, so the dimension of this is d plus 1 cross 1. Okay, and I will have to multiply it with the features. So all the features that are here, x1 to x, so for the first guy you have 1 and x1 1 and x1 2, all this. So I will call like this, right? Maybe I will call this as w0, and it goes all the way till wd, totally d plus 1, like this, x2 3 all the way till xd. Oh sorry, so nobody told me this, but this is just the first feature vector. Okay, so if I multiply this with this, I will get w transpose xi. Okay, so this is the first one, this is the second one, the augmented feature vector for the second data point, this is for the third data point, and all the way till the nth data point. And this matrix I will call it as A, and this row vector I will call it as W. Okay, is everybody able to appreciate this, what this is? When we multiply A times W, I will get a vector of all my predictions. So AW is a vector of my predictions, vector of predictions. Is this clear?
Yes.
Yes, sir.
Yes.
Okay, some people have become extremely quiet, especially from the math department. Mahendra, are you here?
Yes.
Okay, are you understanding everything, whatever I am discussing?
Yes, sir.
Okay, all right. So now what we have to do is we have to change this into matrix notation. So if I do A transpose W, I will get a vector of all the points, right? So let me just try to say, so y minus AW, so if I do y minus AW, what it will be? So that will be y1 minus x1 transpose W, y2 minus x2 transpose. So I should write a transpose here because it is written row wise. So whenever you write something row wise, it is like this. Okay. So this y minus AW is the error that you are getting at each of the data point. What I wanted is sum of all the errors. See, I have forgotten to write the square. Okay, it's the square of it. So how do we write it? How can we convert this to in the terms of matrix notation? What can be done?
So y minus AW into y minus AW transpose.
Yes, not we have to be careful. Y minus
Y
AW.
minus AW transpose to Y minus AW.
Yes. So I don't know who spoke. Was it Sneha? You spoke.
Yes, sir.
So now do you understand? I mean, you have to multiply y minus AW transpose y minus AW, not the way you said. Okay.
Yes, sir.
Okay. So this is our gradient. Okay. Sorry, this is our cost function written in the matrix notation. Why did we write in the matrix notation? You will see when I do the next step. Okay. So this is written in the matrix notation. Somebody has messaged.
Yeah, sir.
Yeah.
For the cost function, in the case of mean, we didn't take the denominator n because it was not required, right?
Hmm.
We anyway have to just minimize it.
Hmm.
Then why are we taking this half again and again?
Uh,
Like,
uh,
isn't this
yeah, it is taken as a convention, but you are right, it doesn't really affect much. Okay. Yeah, you're right. So anyway, now possibly you may understand this better when I do the next step. So what we will do is we will take the gradient of j with respect to w. In fact, we will take the derivative of j with respect to w. Okay. So w. Okay. Let me. Yeah. So this is going to be like, what is this? So I shouldn't write it perhaps this way, but it's actually going to be a row vector, right? Because j is a function. J is a function from r d plus 1. So those of you in optimization would have seen this, but like rd plus 1 to r, when I take the derivative, the gradients will be the partial derivatives, right? So that I'm going to set the entire vector to be equal to 0. So that's essentially what we are doing here. But let's just write this thing in the notation of vector itself. So we understand that this is a vector. So when I take the derivative of this is again something that you have to check. Okay, this is there in Bishop's book. I think some appendix C or appendix D, it has this. So when you take the derivative with respect to w is a vector, what you will get, Siddhant, here is possibly where it will be used. So it will become 2A transpose times y minus AW. Okay. So this 2 and this 2 gets cancelled. So basically what we are trying to say is that A transpose y minus AW is equal to 0. Okay. So now we will try to solve for w using this, because w is the value that we are interested in, right? So what we will get is A transpose y minus A transpose AW is equal to 0. So w is actually going to be A transpose A inverse A transpose y. Okay, so this is the expression for w. Okay. So are there any immediate questions in this derivation?
Sir, is A transpose A always guaranteed to be invertible?
Yeah, so that we will discuss. That's a good question actually. So invertibility of okay, of A transpose A, that is a good question. So we will discuss that. Any other questions related to this? So how do you solve your linear regression problem? What you do, you just take your data points, you write it as A, you do A transpose A, take its inverse, and then A transpose Y is your data points again. So A is a vector matrix of your data points, right? So you do this operation, you get a W that is going to be your best W, which minimizes the error, the mean square loss. Okay, so this is what it is. Now, why is A transpose A invertible? So that is the next question. So let's try to address that. Yeah.
So could you explain that delta J step? How did you get to
Yeah.
A transpose that once again?
Yeah. So see, we are taking, so J is a function from Rd plus 1 to R. Okay. Do you understand this? This is okay, right?
Yes, sir.
And the gradient, when I say gradient of J, it will be a collection of partial derivatives. So del J by del W naught all the way till del J by del WD. Okay, so that is what it will be. Fine.
Yes,
So
sir.
so now this particular step that I did, which gave you this step, is very yeah. So this is something that you have to see yourself, but it's something that is so what you need to do if you want to prove this statement, right? If you want to show that this derivative is 2 times A transpose this, what you need to do is you need to take a small example. You look at y minus AW transpose like this, you will get a function, long function in terms of W0 to WD, take its derivative, you get a value. Do this operation, you will get another value. and it turns out that they will be the same. Okay, so this check how to do, is it clear to you?
Yes, sir.
So this is something that you have to do at your time, because it is just too much algebra. No, we are spending a lot of algebra nowadays in the class, so it's not really productive to do this. Okay, so just for now you believe, so it looks like, see, you look at this, it looks like a function. So there is a minus coming in. Okay, so I didn't write it, but anyway, there is a minus coming in, but that doesn't matter, because when you set to 0 it doesn't matter. Tanuja, it is like your some x, like y minus ax squared, right? If it was a
Yes,
regular,
sir.
yeah,
2
so
into 1 minus x into like whatever is there as a coefficient we write it.
yeah, exactly. So it is somewhat analogous to that. That is the only thing I can say here. But it is just like when you take your derivative, you use first principles to get it. The same way you have to do to get this. Okay, so yeah. So I urge you to do it. I mean, you have to like sometimes at least you have to do this algebra, just so that next time you don't get very scared about it. All right. So now before that, no, before we talk about invertibility of A transpose A, I want to do the other gradient descent approach also, because invertibility will take me some some time to discuss. So we will just keep this space over here free, and then we will talk about invertibility. But this is called as the normal equation approach. These are called as normal equations. I have no idea why, but I should have seen it, because last year also I was wondering why this is called normal equations. But anyway, so this is called normal equations. It gives you a closed form solution for W. Okay, so that was one approach. So remember, so we said there are two approaches, right? So we have done this approach. We want to do the gradient descent approach. So let us go to that. So JW, let's now when I write the gradient descent approach, I will not do the matrix notation. I will try to do it directly, because it is beneficial that way. Okay, so W, I want to remind you that it has W0 to WD plus 1. Okay, so let's try to take its derivative with respect to each of the components. So del J by del W0. So Tanuja, can you tell me what is the derivative for this del J by del W0?
Yes, sir. So 1 by 2 into
Summation will be there first of all.
yes, sir.
Yeah, because for each sample it will come, right? So I equal to
Yeah.
1 to n. Yeah, so 2 times, yes.
2 times minus W.
Minus, no, be careful here. So
Okay, we
see,
are doing with only
two
the,
times, so first this one will come, right? 2 times y transpose xi.
yeah,
Then
and x0.
x0 is what? Is the augmented feature representation, right?
Yeah.
So it is actually xi of 0, but xi of 0 is 1.
Yes,
Okay.
sir.
Okay, so and there is a negative sign, so like this. Is this okay?
Yes, sir.
So likewise for a general wi, so I mean I don't want to write I, but okay, what do I? Maybe some k, right? The kth component here will be again. So it will be exactly similar. You will have w transpose xi minus yi. So this minus half I have pulled in. Okay, I going from 1 to n, xi of the kth component. Okay, so this is what it will be. So yeah, so you will so first of all is this so this is going to be a some number, right? So how do you think about this? This is like the error made on the ith point. Okay, and this is the ith, like the kth coordinate. So basically I'm making like a sum of all the errors we are looking at, and that is the gradient. Okay, so now as before, so we can write the gradient descent version. So what is that? So you choose W randomly, and this is your init, and then loop till j of W doesn't change much, right? So this is like from the previous iteration to the next iteration, there is not too much change. So when you can keep some threshold epsilon, as long as it doesn't change, you can stop. Okay, and what you can do is you can say W of k plus 1 is equal to W of k plus this whole thing, W k transpose xi. So you want to do a descent, right? So descent means minus eta times this. Okay, so your input eta is chosen by you, xi minus yi times xi, yeah, like that. Okay, so this is a vector, so this is a vector, this is a vector, and xi is a vector. So is it clear how the gradient descent algorithm comes? Siddhant, do you have any questions here?
No, sir.
Okay, so somebody else was also speaking.
Sir,
Yeah,
eta will be same for each W, right? Like eta is a single number, or
yeah, eta is chosen. So eta, no, again, yeah, there is a eta's discussion, like how you choose eta. There are various things you can do. So in optimization, there are several techniques how you choose this eta very nicely so that it converges. But what we will do is we will keep it fixed. But whatever you are saying, Advay, actually eta choice can be made to go down with time. Okay, so you can make eta grow to 0 so that towards the end it shouldn't change much. So
yes.
so such things you can do, but there is a theory as to how it can be done and all those things. So that we will not worry. But yeah, but this is essentially the algorithm. Okay.
Also, sir, one
Yeah.
more thing.
Yeah.
Do we look till like J of W doesn't change or W doesn't change? Like both will be the same
No,
thing,
J
right?
of W, yeah, that is true. W doesn't change, also translates to J of W not changing, but I think J of W is something more directly well understood, right? See, W is a price, right? So W is like some price of your thing. So when you look at how much error your algorithm is making in terms of price squared, that may make more sense. But either you can use, there is no such.
Yes, sir.
Yeah. So so here again, so depending upon whether you use all these samples or a portion of the samples, you can get gradient descent or stochastic gradient descent. Okay, so stochastic gradient descent. So you can be implemented by taking a small batch. Okay, so if I take only just one sample, that will be Wk is equal to Wk minus eta times just one. If I am doing, it will be Wk transpose xk minus yk times xk. Right, I'm just taking one sample instead of ith one. I'm just looking at some sample k, looking at the error and making this adjustment. So this, if I do, this is going to give you one kind of stochastic gradient. Okay, so as I was telling you, so I will probably give you an assignment regarding this. But when you have the so this is your, you can plot, for a simple example, you can plot the contours like this. Okay, and you can start with some W and you can see how it will go to 0. So for example, when you do like, it can go all the places like this, and finally it can just be oscillating here. Okay, so this could happen, and this will happen depending upon whether you use gradient descent or if you use stochastic gradient descent. Stochastic gradient descent may just keep going everywhere, right? And then it may just reach here. So all these things you can plot on the contour and see. So I will, these are all easy things, it won't take you too much time, but it's nice to see this once. So that will be something that I will ask you to do. But yeah, so this is regarding this gradient descent. So Yeah, so what we have looked at, this is like we were trying to, so I want you to remember this. All right, so what we did is we were trying to look at linear function as an approximation for yi. Okay, and then that is how we took the difference and set it to 0. Okay, so yeah, so that see, don't get very scared here. W transpose xi minus yi I had written, whereas here I wrote y minus aw. That doesn't matter because it's a square. So anyway, I'm taking the square, so it really doesn't change anything. Okay, so anyway, so this is all the discussion. So one obvious thing we can do, so y belongs to R, right? So what we can do is we can focus on y belonging to 0 1 and then try to do linear regression. So what it will do if I do this,
Why is our result on the house price that we are predicting?
no, this was originally house price, but I will try to do it for some other price. I will some other situation. I will try to do this. If I do that, what I will get? This will be like
Sir,
classification, right?
yeah, then it will become a classification.
Yeah, so that can be done. So that is just some, because we have spent so much time discussing that. I'm just trying to say this can be used for classification, but there is a problem which I want to also tell. So suppose you look at tumors, right? Tumor size. This is a standard example. I just want to make it very clear. Y is so y is equal to, this is like cancer. So 1 means it's cancerous, or 0 means it's benign, whatever.
Benign, non-benign.
Yeah, benign and malignant, I think it's called. But anyway, that's not the here. So you have these points which are tumor sizes which are low, which are not too big, so perhaps not cancerous, and then, or which are benign, and dangerous ones are typically tending to be big, right? So like this you can have, and when you try to learn the function, you will get a line like this, right? This perhaps minimizes this. So can someone tell me what is the problem with this approach?
A lot of points are misclassified.
I mean, misclassified, yes, but I can approximate it, right? So if they cross 0.5, I will say they are all 1. If they are all less than 0.5, I'll say it's 0. So what is the problem? Still it is okay. I mean, I take your argument. Your argument is y belongs to this y. I can have, for example, y of xi to be equal to 1.2, right? What does it mean, right? This is kind of strange. So this is what you are saying.
It can also have some irregularities on an outlier, like it won't be able to handle the outlier much.
Yeah, so that is essentially the problem. Okay, so if you have a point which is like this, and if you try to, this will now have a very large error, right? So in order to minimize this, your learning algorithm may do something like this, right? Something like this, and then it really breaks down, right? Now it is now very strange. We don't know what is happening, right? So this is what I'm telling you here is you can use linear regression for classification, but in the presence of outliers there will be trouble. Okay, so we will look at a better algorithm soon, maybe tomorrow, where this issue is addressed. Okay, so this is a topic for tomorrow. It is called as logistic regression. So that will be, we will finish it tomorrow. But now coming back to the original question, I think it was Satvik who asked it, if I'm not wrong. So how do we know A transpose A is invertible, right? So this question we will answer now. Okay, so first of all, so you are, what is A? So let us try to understand that. So A is, so let me not write in this space, it will be too less. Okay, so you just see next pages or something. What is that? PTO we say, right? So let me write PTO. Okay, so so let's do that here in a proper space. So what? Yeah. So invertibility of A transpose A. So what you have is A is a vector like this, 1, x1, x2. Sorry, 1, x1 1, x1 2, all the way till x1d. So d features of a particular sample, and 1 x2 so d features of second sample, like this. Okay, so you have this. So now one thing that may happen, yeah, so this is like this. So the dimension of this entry, what is the dimension? So there are n rows and n different data points and d plus 1
D plus
features.
1 column.
Okay, so let us so one thing is we have to assume this. So we have to assume that n is going to be much bigger than d plus 1. Okay, n has to be much bigger than d plus 1. Otherwise what will happen? Otherwise you have a situation, for example, right, in the worst case, suppose I'm just going to give you one data point, right, or maybe I will give you 5 data points. So if d is much greater than n, what you have is it's a high dimensional problem. So what that means is for a particular feature I will have lot of details about that individual, right? So for example, I will have height, weight, right, then hairstyle, then I don't know, age, and then BMI, okay, and then shoe size. All these kinds of things will be there, and I only have few. So there is individual 1, individual 2, individual 3, maybe 5 people are there, but there are like 100 dimensions of this, right? So when you have a problem like this, what is the issue? I mean, I have not discussed this fully, but intuitively what do you think will happen if I try to learn this?
Overfitting kind.
Yeah, it will be very what will end up happening is that it will memorize your data set, your function, because you have so much variabilities, right, so many degrees of freedom. See, each w that I add is a degree of freedom. I can choose different w's here, right, w to wd, right, w1 to wd. These are all degrees of freedom. So if you have more this, you will have more degrees of freedom, and when you have more degrees of freedom, you will have this overfitting problem. If you remember, when I talked about that example, if you have this like a line, and there are this all these points which are noisy, if I take a very high degree polynomial, I will perfectly pass through that, right, like this. But it may not be the best approximation to the line, right? So this is the overfitting thing. Why it is coming in the case of a polynomial fit is because you have too many degrees of freedom, too many polynomials that you can choose the values for. Okay, so the same way, this kind of a problem is a it's a issue whenever you have a problem where n is much bigger, d is much bigger than n. You have to do dimensionality reduction. You may have to use clustering, right? You try to cluster and reduce the dimensionality, or you will do PCA. All these things we will discuss at some point, okay? But you have to reduce the dimension, okay? So let's not worry about the situation where d is much bigger than n. Let's only worry about n is much bigger than d, okay? Now if n is much bigger than d, then A transpose A, the dimension, what is the dimension of A transpose A? Can someone tell me?
D plus 1 cross D plus 1.
Yeah, so dimension of A cross A is d plus 1 cross d plus 1. So this will be invertible if the rank of this matrix is d plus 1, right? So if the rank of this matrix is d plus 1, we are done. Then it will be invertible. And how will the rank not be invertible? Can someone tell me when this will not be rank d plus 1?
We can like find a non-null vector which is like in the null space of A transpose A.
Yeah, so that is true. So okay, so that means like what he's saying is you can find a vector in the null space. I don't know who said that.
Karthik.
Karthik, okay, so you have, okay, good, it's CS student has told, so that means you have learnt your linear algebra well, but essentially what you are going to say is that some linear combination of these columns are going to give you the other column, right? Karthik, you have
Yes,
a
sir.
question? Yeah,
Like,
you are,
like
yeah.
we can, like we can derive that fact from what I just told.
Yeah.
So,
But yeah, so essentially what Karthik is saying is that some linear combination of these columns you can add up and you'll get zero. In other words, in other words, in a simpler word, you can get some feature, right? Some feature is there, some feature, perhaps this feature, is it's equal to some linear combination of other features. Okay. So I'm not considering a case where all the features, all the data points are coming from one point. Such cases and all I'm not saying. But all I'm saying is there is, for example, right? What can someone give me an example where this linear combination of features may happen? It's difficult, so let me just say. So you have area in meters and area in feet, right? So they are linear combinations, right? So like that, if you have something, it is going to happen. Okay. So to answer Satvik's question, you should not have features that are redundant in the sense that that information is already present in some other place as a simple linear combination. Then your A transpose A may not be invertible. Okay. Satvik, does it answer your question?
It was my question, sir. Advait. It's clear.
Okay. Yeah. Okay. Yeah. All right. So yeah, Advay, thanks for that. So anyway, so that is what that is. So the two approaches, I hope everyone is able to understand, right? So yeah, so let me did anyone hear about the mid sem exam? Has it been announced or something?
In the academic calendar, it has been mentioned from 7th to 14th, but no data, no time. What do we call it?
Okay.
Exam sheet that has not been declared yet.
Okay. So what I will do is I will assume that it is going to start on 7th. So tomorrow will be the last class unless the examinations get postponed. Okay. So if the examinations are going to happen from 7th, then of course tomorrow will be the last class. Otherwise, I will take next week as well. So it depends upon how the exam week is. Okay. So I will try to, as promised, I will give you 1 week off before the exam. So anyway, so that is what it is. Okay. So this entire discussion was with the view that I am trying to minimize half summation W transpose xi minus yi squared. So this was this view, and this gave us two approaches. That one approach is A transpose A inverse A transpose y. So this was one approach. The second approach was gradient descent. The gradient step is kind of interesting. So what it is saying is you look at W transpose xi minus yi times xi. This is your gradient, right? Eta times negative. So W k, this will be wk plus 1. So something like this update you do. Okay. So I hope this step is correct. I don't know what it was. Anyway, so that's fine. So if it is not, just adjust it. But anyway, this is just the one view. Now the other view I want to just emphasize, and we will stop at that view, is that there is a probabilistic interpretation as well. Okay, so what is that? So what we are saying is, suppose if you imagine another model, the model is as follows. You have that y is a function of x as the following. So y is equal to W transpose x is given, but there is some noise. So that means when you look at this point, it can be this, but there can be some noise here. So we assume this noise to have some feature which is epsilon will be normal with the mean 0 and variance epsilon squared. So the assumption is this, right? So y is equal to w transpose x plus epsilon, where epsilon has this normal with mean 0, variance sigma squared. Okay, so this is suppose if you have this model, what you can do is you can actually
Sir, here is sigma a random variable as well.
so sigma is assumed to be known. Okay, so this is assumed to be known.
Okay, sir.
So it's assumed to be known, rather than that I will say it is assumed to be fixed. Okay, it's not a random variable. That's what you are asking, right? Yeah. So there are
Yes.
variations. There are variations of this algorithm where you assume like even this is uncertain, and all those interpretations are there. We will be doing that in the class at some point. Okay. I think I suddenly saw the time is quite late. So let me just very briefly say what this will give you. So what we will do is we will assume this probabilistic model, and then we will try to learn W as MLE estimate. Okay, we will try to do this tomorrow as MLE estimate. We will try to learn W as an MLE estimate, and that also in turn will end up being having the same formulation. It will end up giving us the same objective function. So that is for tomorrow. We will discuss this tomorrow. Okay, so let me stop here. If you have any questions, you can stay back and ask. Yeah, so thanks everyone.